How are we doing? That good, huh? I did have someone grade the homework for me, so if you've got questions about the grading, about anything, please feel free to contact me. I'm happy to go over anything with it. There's also an answer key on Moodle as well. So, but like I said, if there's any issues, if there's any adding errors or what have you, just tell me. We'll have to look at it. All right. New assignment here. Your first exam is Friday the 19th, so let's just go ahead and make it due with your exam. That way you don't have to worry about not 9, 2/19. Say that again. Yeah, there's a topic that goes along with section 1.7 that's towards the end of your book, so that's why there's a nice large jump between those two. So that really is page 518. Thank you for mentioning that, though, because I really did mean to mention that. I really did mean that number. All right. Any questions about anything at all? Before we get into some new stuff. All right. Well, let's talk a little bit more about matrices being invertible. We started with that list last time. We're going to add a couple of more conditions to that list as we go along here. A couple more today. We'll have another one or two in the next chapter, I think it is. But anyway, a lot of this goes into, like I said, for linear algebra, it's talking about solving systems of linear equations. And the next couple of things that we're going to talk about as far as being that equivalence statement that we have, that long theorem that I told you to write on a separate sheet. We're going to have a couple more that deal with solving equations. So just go ahead and add these in here as we go here. So along with your list of theorems, this go along with the concepts that we talked about with solving systems of linear equations. I believe we're on E as far as the list goes. So we've already had a statement about invertibility that had to do with solving a homogeneous system and saying that if you can solve the homogeneous system and it only has the trivial solution, then the matrix had to be invertible. So if you had the AX equals 0, then it had to be invertible. We can actually say that for non-homogeneous systems as well. This would be, say we had any matrix B that we wanted. This is going to be consistent for any matrix B that we want, as long as it has the right size. Now, before I write the next one down, let's just think about why this one might be true. So if it's invertible, we already talked about this before in the last class period. If it's invertible, what can I multiply both sides by to get x by itself? Yeah, A inverse, right? So consistent again means that it has at least one solution. So certainly if it's invertible, it's going to have at least one solution, right? Without any doubt, right? So certainly this statement's true if it's invertible. The next one's a little bit stronger. This says that AX equals B has exactly one solution. For any n by 1 matrix B. And certainly the fact that a matrix is invertible would certainly give you this statement as well, right? Because if you know it's invertible, you can multiply both sides by A inverse, and you get A. The only thing that X can be is A inverse times B, right? So certainly, if it's invertible, remember this is the whole point of that theorem that I told you to have that list of properties. The whole point of that theorem is that any one of the statements implies any of the other statements. Logically, they say the exact same thing, right? And we said that to be able to prove those kind of things, we go in circles. Okay? So certainly, if it's invertible, we get exactly one solution. If there's exactly one solution, certainly that would imply that this works, right? If it has exactly one solution, it's certainly consistent. So we get A implies F, F implies E. So to complete another circle, we would do E implies A and finish off the circle, right? Well, if it's consistent for any matrix that we want, then we make certain ones. So if we wanted to do E implies A, so we suppose that this is consistent for any n by 1 matrix B. Let's consider the following systems. Let's do AX and then equals the column vector that has a 1 for the first entry and zeros below. Let's do the exact same thing except shift that 1 down a unit, or down a component, down an entry. Do the exact same thing but switch it to the third spot, and so on down the line, until we get to putting that 1 in the very, very last spot. So according to what we're supposing here, is that we can solve each of these equations that I just wrote down, right? Right? I can certainly solve each of those equations. So I'll just write down that there exist solutions. I'll call them X1. I'm going to call them C. C1, C2, out to Cn for each of the respective equations. I'll call it B, be the following matrix. So basically what we're going to do, we're assuming that we have a solution for each of the equations. We're going to make up a matrix. Remember, the whole point of this is we're trying to get to the fact that A is invertible, right? To show that this is, to show that the statement being consistent for any matrix that any column matrix that we want is implies the fact that the matrix is invertible. We want to get to the fact that the matrix is invertible. So I need to create a matrix that I think is its inverse. Okay? So that's where these equations are coming up, right? to be the inverse, I have to have something to get me the first column of the identity, something to give me the second column of the identity, and so on down the line. So I'm going to create the matrix that has columns that are the solutions to these equations. Okay? So now when you take A times B, pardon me, when we take A times B, that's A times this new matrix that we just formed, let's think about how we can do this product in chunks. Let's think about, I like to think about it in chunks, for lack of a better word. Think about how each of these things would get multiplied. So you would take the first row of A and multiply by the first column, and that would go up in your first entry here, right? Then you would keep going down that column. You would take the second row of A, match it up with the first column, and put that in the second entry here, right? And so on down the line. So if I think about it in chunks, I can think about taking this A times the first column, that becomes the first column of the product. I can take the A times the second column, that becomes the second column of the product. And so on across the columns. So I can think of this product as being A times C1, A times C2, and so on down the line, A times Cn. What do each of those columns now have to be? What's the first column have to be? Which equation did C1 solve? The one with the 1 on the top, right? So this has to be 1, 0, 0, and down to 0. What does the second column have to be? Good. And then so on across until I get 0, 0, 0, all the way down to 1, right? What matrix is that? The identity. So I multiplied A by something, you got the identity matrix, so what better A be? Or what better B be, I guess, in return in terms of A? The inverse, yeah. Okay, so I just wanted to go through that to see why the fact, well, in particular, to show that we really did have being consistent for any matrix we want really does imply the matrix is invertible. But also this idea of how we can do this type of almost a block, there's a concept called block multiplication in matrices, that if you can block it appropriately, you can make some of your products simpler. So this is one of those examples that we're going to come back to later on, that the fact that if I take a matrix on the left and multiply by these individual columns, I get the matrix times the column in each of the columns. It's just a way to express the product a little bit simpler. I could have done an equivalent idea if I would have had rows on the right and a matrix on the rows on the left and a matrix on the right, and I could figure out the rows in the same fashion. All right. Anyway, that just was the last little thing I think we need to talk about in that particular section. Except for one more theorem that I'm not going to bother going through. I will mention it, though. It pops up. It does say that if you have a product, if A and B are square matrices such that the product is invertible, then the individual pieces are invertible as well. This one, just to give you a taste of why this has to be true, let me just go through part of it here. So it's the reverse idea, right? We've already talked about that if A and B are invertible, then the product is invertible. And we actually know how to do the inverse of a product, right? If you have AB and want to do the whole thing inverse, how do you rewrite the product? How does the inverse distribute over the product? What do you have to do? Close. It's the B inverse A inverse. Remember, you have to reverse it, right? So if you do the inverse of the product, you have to do the product of the inverses, but it's reversed, right? Okay. So we already know if the individual pieces are invertible, then the product is invertible. This does what's referred to as the converse, right? Okay. So if we suppose here, basically I'm going to show that B is invertible. Okay. Suppose that AB is invertible. So let's let C be the inverse. I'll just use it as C as opposed to the whole thing. But let's let C times AB be the identity. Instead of writing AB quantity inverse, I'm just going to call it C. Just for basically just so I don't have to write AB quantity inverse every time I want to refer to it. Okay. So now let's consider the following. Yeah, consider the following. Exactly. Consider the following. All right. So we're going to consider the equation Bx is equal to 0. From the theorem that we've been creating, that big long one, if we can show that the only solution to this is the trivial solution, if we can show that the solution to this is x equals 0 and that's it, then what does that say about B? It's invertible, right? That's one of the conditions, isn't it? So if I can show that I can get this down to x equals 0, then I'm done. I know that B has to be 0, right? Or B has to be invertible, I mean. Okay? So to get to that point, what am I going to do? Well, I'm going to multiply by A. I guess I didn't need this. Well, I guess I didn't need the C in this particular case, but I can yeah, I did. If I multiply both sides by A, what do we get? Well, I get A times B times X. I get A times 0 on the right-hand side, but what is A times 0 going to be? 0. Now, I'm not quite to the identity here. All I know is this is invertible. However, now multiply both sides by C. I still get 0 on the right-hand side when I do that. Don't I? Right. First, I multiply by A, basically because I know something about AB. That's why I multiply by A first. What do I know about AB? It's invertible, so it has this inverse that we wrote down as C, right? So then I multiply both sides by C. What can I do on the left-hand side? Yep, so I can change this to CA. Oh, I can change the whole thing to I. You're right. C times A times B is just I. Good. And so I get x equals 0. Well, I should write it as Ix equals 0. and then I get 0. So what that tells us is that since the only solution to bx is equal to 0 is x equal to 0, we have that b is invertible. So that gives us an example of how we can use that theorem to show something's invertible without actually finding what its inverse is, right? We never did write down what the inverse of b was. We used the theorem that says that having only the trivial solution to the associated homogeneous system is equivalent to being invertible. That's how we got there. So again, just looking at the steps that we did, we assumed it was invertible, wrote down what its inverse was, and then I used this property here. Basically, I used this equation and built up the left-hand side until I could cancel it out, right? First multiply both sides by A, then multiply both sides by C until I could cancel that left side out. Never actually having computed the inverse of B at all, I know it has to exist. And then once I know that the inverse of B exists, I can multiply AB by its inverse. And I know that the product of invertible matrices is invertible. So AB times B inverse is going to give me A, which has to be invertible, because both pieces work at that point. So we can get to the fact that they both had to be invertible, which is nice, right? It's not possible to have something that's invertible and be able to break it down into pieces that aren't. You've done things with breaking things down into pieces since you were in grade school, right? So one of the things else that we're actually going to talk about breaking down matrices into pieces as well. This here, what we're going to jump to in chapter 9, which is at page 518. We're going to talk about breaking matrices into pieces and then analyzing the different pieces. And you've done that since grade school. You've done factoring numbers, right? And then in algebra, you factor polynomials, right? And here we're going to factor some matrices and talk about how you can look at the individual pieces to give you something about the whole, the thing as a whole. We're going to talk about, in some sense, factoring vectors. But what does that mean necessarily? We'll talk about factoring is not really the right idea, but it's the same kind of thing, breaking it down into pieces and then analyzing the pieces. Okay? One of the things that we're going to talk about later in the semester is looking at long-term behavior of something. And to do that, we've got to break it down into pieces. Talk about some of that stuff in chapter 7, I believe it is. Okay. But you've done this before. You've broken things down into pieces, which is exactly what we're talking about here. We've got a matrix that if we know it's invertible and break it down into pieces, the individual pieces have to be invertible as well. One of those types of factorizations we've already talked about is factoring it into elementary matrices. We did that last time, right? Writing the matrix as a whole, if it's invertible, as a product of its pieces. And we're going to do a little bit more, but we're going to do an application of that here in a little bit. All right. Questions about either of these two results, at least, that we've talked about? I know it takes a little bit of time to kind of absorb the proof. I'm not expecting a full understanding of the proof as we went through it, but does the results make sense what we did? If you have something that, basically, if you think about invertibility, if I have something that I can undo the multiplication by, I get a unique solution. Right? That was the first thing we talked about. And this is just that if we break it into pieces, the pieces have to behave nicely, essentially. All right. Well, let's go on to section 7 then, which talks about triangular matrices and symmetric matrices. And it's really we're going to talk a little bit about the symmetric ones That's going to come into play later with least squares idea that we'll talk about later in the semester. Symmetric matrices will pop back up again. But for our application purposes, the triangular ones are the ones that we're going to be interested in for our purposes right now. So the names kind of give away what they are. We've talked a little bit about diagonal matrix to start with. Diagonal just means, by the way, these all have to be square. So everything in this section, everything's going to be a square matrix. We're not going to have anything that's not square. Okay. As far as the definitions here. Diagonal just means that your main diagonal here is the only places where, I usually write it this way. The main diagonal is the only places where you might have something that's not zero. Everywhere else there's a zero. Literally it looks like a diagonal, right? So as a technical definition, I'll write it down. An n by n matrix I'll say A, and then write it as a general entry, is diagonal if A sub ij is 0 whenever the I and the j are different. Again, thinking about it in terms of the subscripts, the diagonal entries are the ones that have the same subscript, right? So this definition says that if you're not on the diagonal, if the subscripts are different, then the number had to be 0. Okay. So what's one of the properties, or what's a couple of the properties that we're interested in for diagonal matrices? And these will pop up again later in Chapter 7 as well. It's one of the things that's going to allow us to talk about long-term behavior of, say, matrix multiplication, for instance. So what's a property of diagonal matrices? Well, let's just do a specific example or two and then write down with a general idea. So let's say I have the matrix, let's say I do 3, 0, 0, 0, negative 2, 0, 0, 0, 5. And now the matrix on the right here, I'm not going to worry about it necessarily being square, just that I can actually multiply it. So let's say I have a 3 by 2 here. Let's say we do 1, 6, 5, negative 1, and 3, negative 8. So let's see here what we get when we do the multiplication. And we're going to write down the numbers, but let's just be a little bit more analytical about it and see what's really going on when we do the multiplication. So the first thing we're going to do is match up this first row and multiply by the first column. What's the only product we really have to do? The 3 times the 1, right? The other ones are going to get killed by the zeros, correct? And notice when you do the same thing with the next column, if I take the 3 and multiply it down the next column, the only thing I'm going to have to do is what? The 3 times the 6, right? So notice that, and I'm going to write that out longhand as opposed to actually computing it right this second. I get 3 times 1 here, and that's it, right? 3 times 6 here, and that's it. Was there anything special about the 3, the 1, and the 6? I mean, besides the fact of where they are. Did the numbers matter? No. Had this been a 4 and this been a 2, it would have been 4 times 2. Right? The numbers itself didn't matter. Notice that the important thing to notice here is that this 3 basically gets distributed across that row. Right? You see it? If I had another column here, would the same thing happen? If I had another column, would the same thing happen? Yeah. So basically, when I've got this first row here, when I've got this 3, 0, 0, I'm basically just essentially distributing the fruit across it. Right? What happens in the next row? What are the only products you're going to do in the next row? Yeah. So notice in the next row, I've got the 0, 2, negative 2, 0 is going to match up with the 1, 5, 3. The only product you end up doing is the negative 2 with the 5, right? So you have a negative 2 times 5 and a negative 2 times negative 1. Again, did the numbers actually matter? No. If I added more columns on, would you get the same form for the products? Yeah. So again, it looks like the negative 2 just gets distributed across the row. And then likewise, in the last one, you're going to get a 5 times 3 and a 5 times a negative 8, right? You see it? So these diagonal matrices, when you multiply them on the left, when you multiply a diagonal matrix on the left, it just ends up taking that diagonal entry and distributing it across the corresponding row. If you've got what that tells you is that if you've got a diagonal matrix in your product, it saves you some computations. You might actually have to do this 0 times the things, right? You have to distribute it through. If you're thinking about doing things from a computing standpoint, a programming standpoint, saving computations can help when you've got large things, right? There's a whole bunch of different techniques for doing things with what are referred to as sparse matrices. Sparse matrices are ones with lots of zeros in it. If you've done any discrete math before, you might have done adjacency matrices for graphs. And if you've got a really big graph with not a lot of edges in it, that adjacency matrix is going to have a bunch of zeros in it. And you know from work that you've done in graph, if you haven't talked about graphs before, you can ignore everything I'm saying. We haven't talked about it in here. But from stuff that you've done before with graphs, you know that if you do a power of that adjacency matrix, it tells you, can you get from one vertex to another from paths? And then do another one, and it tells you if you can get through there that way. You can calculate lengths of, or what the shortest distance is between any two things that way, for example. That's a lot of computations from a matrix standpoint by doing all those products when you're doing powers, right? But if you can eliminate some of them by getting rid of the zero products, you can save yourself a lot of computational time. Again, like I said, if you haven't talked about that stuff at all, you can ignore everything I just said for the last 45 seconds. Okay? But to give you an idea of why you might care about such things, if I can put a diagonal matrix in my product, I could cut down a lot of the products that I have to do. Okay? So this is one of the things that we're going to talk about later on is when can you put a diagonal matrix as part of your product and do a lot fewer computations. Okay? This is stuff that we're going to talk about later, which is why we're interested in it now. All right. You might have noticed in the middle of my rambling there, I said, before I started doing that rambling, that I multiplied this on the left. Let's do a multiplication on the right and see what happens with a diagonal matrix. So I'm going to use a similar matrix, but I'm just going to transpose it so that the product actually works. So let's just do the transpose of this matrix and then put the diagonal matrix on the other side. All right, so let's look at that upper left-hand entry again. Look at that upper left-hand entry again. If we take the first row and multiply it by the first column, notice we get the 1 times the 3, right? Now notice in this one, if I take the first row and the second column, the same thing doesn't happen. The 3's not there, right? But what if we take the second row times the first column? You know, what's the only product we would do? You know, the 3 and the 6 again, right? So notice that first column. In the first entry, in the first column, we've got a 1 times a 3. And in the second one, we've got a 6 times a 3. Again, just like I mentioned with the other product that we did, do the numbers matter? No. Notice again here, though, that this entry is getting multiplied down the column this time instead of the row. Is the same thing going to happen with your -2? Probably, or I wouldn't be going through it, right? But the same thing happens with the -2, doesn't it? The -2 gets matched up with the 5 in the first row and the -1 in the second row, right? So you're going to get 5 times -2 and -1 times -2. And then notice in your third column, you're going to get 3 times 5 and -8 times 5. So notice when you multiply on the right, in this case, the diagonal entries get multiplied down the corresponding columns. Okay? And it gets basically distributed down the column. So multiplication on the left goes down goes across the rows. Multiplication on the right goes down the columns. And again, the whole point of this is to be able to speed up the computations that you have to do. Right? There's not a lot of other call to do it besides trying to speed these things up. Because otherwise you can just go run through it all again. All right. And again, this is true in general for any diagonal matrix that you have. Okay. Which also allows you to do things like take powers quickly. If your A was, let's say, 1, 0, 0, 0, 0, -2, 0, 0, 0, 0, -1, 0, 0, 0, 0, 3. What would A to the 4th be? Well, let's think about it. You're doing a diagonal matrix times another diagonal matrix times another diagonal matrix times another diagonal matrix. We can think about them all being on the left if you want to. We just said that this if you take this one times on the left, you would multiply 1 times everything, right? Just on that first row. Well, the first row is just a bunch of 1s, isn't it? Or 1, 0, 0, 0. So you would do 1 times 1, right? And then you would get another 1 and another 1. Likewise, the same thing would happen on the second row, the third row, and the fourth row. So you just end up having to do powers of the diagonal. So this will be 1, 0, 0, 0, 0. What would you get? 16, 0, 0, because you get 2 to the 4th. You would get 0, 0, 1, 0, because -1 to the 4th is 1. And 0, 0, 0, 81. Notice that the power can just go down the diagonal. And again, it saves time. You see why that's the case, by the way? I know I kind of jumped over it. Can you see why we just have to do the power down the diagonal? And again, it just makes it simpler to be able to do these products, which is kind of the point. All right. Let's talk about general triangular matrices. A diagonal matrix is a type of triangular matrix. And the idea here, just to draw the picture for the example I just wrote, the reason why we call it a triangular matrix is because of triangles that we see here, right? I see a triangle of zeros here. I see a triangle of zeros here, right? So a diagonal matrix is a type of triangular matrix because of those triangles of zeros. Okay? So we have two other types of triangular matrices based on where the non-zero entries are. Okay? So we have what are referred to as upper triangular matrices and lower triangular matrices. So let me just write down an example of each, and then we'll write down an actual formal definition. So one that might be upper triangular, again, these have to be square if you're going to be triangular to begin with. They have to be square. So for upper triangular, that means that thinking about the main diagonal, if you will, as a dividing line, the only places where you can have non-zero entries are on the main diagonal or above. That's upper triangular. Okay? So an example of something that might look like that would be 3, 0, 2, 5, 0, 7, 1, 2, 0, 0, 0, 6, 0, 0, 0, 14, say. So here is your, to see the triangle that we're talking about, I said notice these triangles of zeros. To see the upper triangular piece that we're talking about, you've got this triangle of zeros down here. The upper triangular piece is, here's your main diagonal, and above the main diagonal. So there's the triangle. Everything outside of that triangle is 0. It does not say that everything inside the triangle is not 0, by the way. It just says that if you're below the main diagonal, in that lower triangle, everything is 0. Okay? That's what upper triangular is. That if you're below the diagonal, you have to be 0. So it's basically talking about the shape of the non-zero entries, if you will. You can do lower triangular in the same fashion. Lower triangular. I'll do a smaller matrix this time. I'll say 6, 0, 0, 4, negative 3, 0, 5, 7, 2. Again, here's your main diagonal. This is your lower triangle. It's the only place where there's non-zero entries. So that, again, that upper triangle, if you will, is 0. So what I drew up here is basically this is your upper triangle, this is your lower triangle, right? To be upper triangular, you would think about filling that triangle in, right? To be lower triangular, instead you would fill in that lower triangle. So if you want to write down the actual definition, we would write it in terms of the subscripts again. All right, so let's think about the subscripts. I'll just write them in here. See if I can. So this entry here, what would be the subscript on that entry there? 2, 1. And let me just pick out another one. This one would be, I think I'm down in the fourth row, right? 4, 3, yeah. Or this one would be 4, 1. Are we noticing any pattern between the subscripts for anything that's down here in this lower triangle? Okay, so yeah, the first subscript is bigger than the second one, right? Okay. So for the definition for upper triangle, that's how we would define it. An n by n matrix, I'll say A equals Aij, is upper triangular if a sub ij equals 0 when the first subscript is bigger than the second. All right, so let's look at the other one here. Again, if we think about the entries, what subscripts what would be your entry here? I just call it B. What would be your subscripts? 1, 3. Or this one would be 2, 3. And what are you noticing about the subscripts there? The J is greater than the I. Good. So for this one, we would just revert. Basically, you're going to write the exact same definition, just change upper to lower, and this greater than to the less than. So an n by n matrix A is lower triangular. Oops. If a sub ij is 0 when I is less than j. All right. So that gives you the definitions of these things. So we'll talk a little bit next time about some properties of these. And then we'll jump into where the chapter 9 stuff is coming in, the stuff that's on page 518 for homework. It has to do with being able to write a matrix as a product of two things, a lower triangular piece and an upper triangular piece, and how you can use that to solve systems. And again, the whole reason for doing this is to try to cut down on computations. Okay. So we'll talk about that next time. We'll also talk a little bit about symmetric matrices as well. So have a good one. We will see you on Friday.